and it's a pleasure to have you here, Siddharth. And I know you've
Thank you,
done a lot of
Nishant.
work in the green hydrogen field as well. And it's good that we have somebody like you who understands the larger value chain, right? But going into applications of green hydrogen, going beyond refining and ammonia, we do understand there's a lot of opportunity for green hydrogen and for this market to evolve as well. So I'll pass it on to you. I don't know what you have prepared for us today, but I know it'll be valuable for everyone who's given their time out. So over to you, Siddharth. Thank you very much.
Thank you, Nishant. Glad to be here. So what we are planning, I have some, let's say, 7, 8 slides that I want to talk about today, which will give an overview of, what are the uh, overall status in the sector, what are the drivers of the green hydrogen mission in India, what are the inhibitors. Then I'll talk a little bit about the volume of projects that are today and what is the progress on that. And then we will deep dive into the various use cases that are there currently in those projects and what are the new and novel cases. And today we want to focus on glass and storage. So I'll take you through the value chain of glass and talk about where glass is coming. We have tried to sort of give a quantification of that. And then we would also talk about the locked-up storage a little bit as to what could be the value there. So that's what we want to cover. These are 7, 8 slides, so we should be done in 10, 15 minutes. And you're, of course, more than welcome to sort of ask questions and contribute and share your knowledge with the larger group. So first is, what is driving the growth of green hydrogen in India? And the main reason are the government policies that have been coming up. So government has an emission target that they want to reduce the emission intensity to a level which is 45% below that was in 2005. And for that, they need to adopt renewable energy. The government needs to adopt renewable energy and introduce renewable energy based products all across the value chain, across all different industries. Then there is the specific policy to promote green hydrogen in India, which is uh, for 5 MTPA target, and that has been announced from the Red Fort by the Prime Minister, followed by a lot of the work that has been done by the ministry in order to sort of give incentives on the supply side, then creating a site program which gives specifically says that there will be supply chains that will be developed, storage, transportation, distribution of green hydrogen will be promoted. There will be incentives that will be given for pilot projects and R&D. And this is where, some of these novel use cases can come in that we are talking about today. And then there are, specific, sectors such as blending in furnaces, storage, and use of e-fuels, which are given very specific thrust in that program. Now, on the other side, there are inhibitors that, the economics of green hydrogen has been very high. And in spite of a lot of earlier projections that were there, the numbers have not, sort of come out to be a bit lower than what was being hoped. So there is a little bit of a pushback in terms of whether it is the right time to go now or not now. And this is exacerbated by the fact that, when the economics are not working, you need scale to bring it down. But there is no firm obligation from the government on green hydrogen obligation and targets, which could, sort of say that the fertilizer companies need to have an RPO of this. Then, the steel industry needs to have a renewable hydrogen obligation of this much. So that's not there. So that creates a bit of a ambiguity whether there is demand or not. And companies should invest in scaling and reducing the cost. The second inhibitor is the lack of clarity on implementation. So the nodal agencies which are administrating this regulatory framework related to hydrogen are understaffed, and that's where there is a lot of groundwork that is needed to sort of bring them up so that implementation can go on in states like Maharashtra, Gujarat, Karnataka, Kerala, and so on and so forth. There is a lot of policy work that is going on, but that will take some time to get implemented. Then the other part is the missing of the midstream infrastructure. We talk about the end applications, let's say, fertilizer, refinery, glass, storage. We talk about hydrogen production, which is electrolyzer technologies, hydrogen plants. But the midstream infrastructure for storage, transportation, they require quite a bit of focus, quite a bit of development. And right now they're sort of not having that dedicated focus, which leads to a lot of cost surprises for a lot of players, especially the ones that we are working with. Then there are no incentives for cleaner fuels, which reduces, the market for distributed green hydrogen, and there is no clear pathway, to reduce production cost of green hydrogen in the country. So all of these issues have been highlighted, and I think over a period of time, these will get resolved and the market will start to move on. As of now, today in the market, if you go to the next slide, you will see that the currently, in 2024 calendar year, there is not going to be a lot of hydrogen production that will come online. We expect that this will also be the case in 2025, where additionally around 10,000 tons per annum will come online. And after that, we believe that, because of the site program and all the timelines that are under the site program for hydrogen production, the capacity increase should go up significantly to zero point 0.9 MTPA. Now, this is subject to, getting an offtake agreement, especially in the foreign market. We have started to see some of that traction right now, so that will continue to grow. And in 2027, it should double to 2 MTPA, and the government target remains 5 MTPA. So somewhere around 2 to 3 MTPA should be where we should be in FY 2030. If you look at the split of these projects, where are they coming from and what stage are they developing from? So there is around 2.5 MTPA of projects which are announced that they're going to be coming up in India. There are zero point 0.7 MTPA, 700 KTPA of projects, 700,000 KTPA, 700 KTPA of projects which are under construction at various stages of development, and less than half KTPA has been commissioned so far. And when you look at the largest chunk of it, it's coming from the export market and for some sort of refinery usage and so on and so forth. And green chemicals is an emerging area which remains a very small market as compared to the other. So this has been not done to scale, but to show these sectors in a big way. Similarly, as we go along, we expect, even from looking at the project status right now, that around 3.5 MTPA would be what we will reach in 2030, especially the export market takes up. And that remains a bit of a question mark today, considering, how the economics are panning out, but that's the jury is out. But if we now step back and we say that, okay, let's look at, what are the applications overall in the hydrogen market. So we have developed a new graphic here to sort of show how the market works. So how to read that is that we have three levels. One is the use cases, which is how the hydrogen is to be used. Second is the industries in which the hydrogen can be used. And third are the outputs in which the hydrogen can be supplied. So this picture gives you quite a comprehensive idea as to, where do we see an application for hydrogen or a derivative of hydrogen, and what sort of business development that can be done both in India and abroad. So this is for hydrogen syngas market in Europe, but it can also be global. But if I were to give you a voiceover around that, so we have three main levels. That is, green hydrogen and syngas can be used for the production, where it is used as a feedstock that hydrogen goes as part of the chemical reaction that leads to the end product, and it's a major part of the chemical reaction. It's the feedstock. It's the raw material on which the entire product is built. Then the second application is where it is not a feedstock, but it's only used as part of a process as an agent, catalyst, intermediate. It's to enhance the process. It's a critical part still of the process, but it's not the main raw material. It is an enhancer for the chemical reaction, and hence something which could be a little bit easier to decarbonize as compared to really taking the entire feedstock, which is a lot of volume and takes a lot of engineering and everything. And then the third case is, which is the more novel case where most of the volume in Europe is projected, if this kicks off, is the heating, blending, and co-firing use case, which is where we use this as a fuel as compared to a chemical, which is an enhancer, or as a feedstock, which is raw material. So as we go from left to right, this sort of criticality goes down, or the substitution sort of goes higher as you go from left to right. So as a raw material, you require it, and then you use maybe gray hydrogen to do that. But then there's a cost pressure. As a process gas, you have some use case there, and then you sort of can substitute it. It's easier, and you do not have a lot of volume in that. And then heating firing has a lot of volume, but again, it's very substitutable. And in production, if you go to the next level, what are the main industries? We see that as a feedstock, hydrogen is used in the fertilizer industry. It's used in the refinery industry. It's used in the chemical industry, which is a new use case which is developing, and it is an e-fuel, segment, which is again a new segment application in which hydrogen is used as a feedstock. So in the fertilizer, it is used as a feedstock for production of ammonia. In refinery, hydrogen is used as a syngas and is used as for the production of methanol and biodiesel. In chemical industry, hydrogen is used for production of methane and in the production of methanol as a syngas derivative. Now, syngas is important. I will come to that later, why we are talking about syngas here. It's again something that can be produced from green hydrogen and utilizes carbon dioxide, but we'll come to that. And then there is e-fuels, where sustainable aviation fuel is used as a syngas as a feedstock, but it can also be used as hydrogen as a fuel with a fuel cell. So these are some of the production and feedstock applications. And in the process gas, you use it in iron and steel for the production of steel. Sorry, does anybody has any question? So yeah.
So that I think it was just somebody with your mic on. Please carry on.
And then on the process gas, which is used as a catalyst or intermediate gas, you use it in reduction of iron ore in the steel process. You use this for the hydrogenation process in crude oil refineries for the refining process in petrol, diesel, similarly in the food industry and in ceramics, which is also where glass is industry in which you use. You're using it as a process gas. We will double click on this as we go along. And then in heating and firing, you use it in power plants for power generation and long-term storage, as an industrial furnace to burn it as a fuel. Here again, glass has a usage. And in the case of domestic gas, where it is used as blending for natural gas grid, or we use it with fuel cells to power our homes. That's what the different applications are coming up with. In our case today, we talk about glass and long-term storage, right? And just to give an idea why we talk about syngas here, because one of the, if the feedstock is syngas, it can be something that can be produced using the SOEC electrolyzer. There is a lot of research going on, and that's where a lot of application comes in the syngas production there. And that could be a market, that could be a process differentiator. So that's why ability to produce syngas through an electrolyzer has a lot of value, but also in some of these other parts where, let's say I use alkaline or PEM and there's a carbon dioxide process that is running, I can run carbon dioxide plus green hydrogen to capture the carbon hydrogen into a syngas or a methanol process and use it to capture the carbon dioxide. So this is also very important when you talk about industrial application. If the carbon dioxide can be utilized, that becomes very useful. Unfortunately, in the cases that we are discussing today, we do not have a use case of carbon dioxide, but that's where the applications are. So three broad use cases: as a raw material, as a chemical agent, as a co-firing, heating and blending. Within the process usage, there is a requirement for glass. And in the heating and firing, co-firing, we have both for glass and hydrogen. It's not going to be used as a raw material in the production of glass. Then, if you look at the glass industry, where we are double clicking further on the value chain to show where it can be used. So on the, this is how the glass manufacturing process is. So you have the batch mixing, then you sort of melt and, refine the batch of silica, then you condition it, then you get into a forming process, annealing process, and polishing and finishing process, and then there's an inspection and testing. So what happens is that in the melting and the refining process, there is a lot of natural gas that is used. Currently, India is importing all the natural gas that is used in this process. There is, if you talk to glass manufacturers, they are really paid with the kind of cost that they get, even if the gas is coming as LNG at $10 per MMBTU, it is coming at $14 per MMBTU at their doorstep. So that makes them very, very painful. And if you especially want to go for a smaller batch, especially if you want to use hydrogen in the forming and the polishing and finishing process, then the cost of hydrogen is even higher because you are using it as only as a very small volume. So there the price might go up to $20 per MMBTU. So that becomes a very good opportunity to go in and start discussing businesses around that. And that's where, you see some purification of silica and optical fiber fabrication companies, which have a margin, in the larger picture of schemes to sell it into export market with a bit of margin. They are sort of saying, okay, let's try to do that, market our product and a green product, and that's where it is working. So small batch use case, very expensive, LNG, very difficult to get it on time. So that, but the process is very, sophisticated. So you need to run that. So that's where you see some use case coming in. But in the traditional glass industry, which is very, very competitive, and there's a lot of pressure from Chinese glass prices, the use case has been subdued. Although you would want to see that, but we have not been able to see that market adopting it because of the pricing pressure. But in the optical fiber market, for example, it is there. But if you were to quantify that, so around 110,000 tons monthly flat glass production happens in India, and there could be a 440,000 tons per and 440 tons per annum hydrogen requirement for fuel blending, which is 5 to 10% blending if you were to do in natural gas. Again, this is something which is 5 to 10%, and people don't get it. It's $14 per MMBTU. There's a glass export. If somebody is doing that, they could buy it. But we are not seeing a lot of glass export happening from India. In fact, there's a lot of import from China, and hence the prices are down. So people are not that keen. But in the optical fiber industry, on the contrary, because it's going out, there is purification and polishing process where this is required in small batches, price is high, it's going forward. So that's on the glass industry. Then on the long duration energy storage, we uh, have been doing some analysis around what is the sort of RTC outlook for the Indian market, as to how many projects will be based on battery storage, pumped hydro storage, and so on and so forth. So overall, we believe that, the larger picture market is around, for long-term seasonal storage will be around 70 gigawatt. If India's electricity demand continues to grow at the 6-7% per annum growth rate driven by industry, there is going to be a lot of wind and solar that would be required. But the problem is that with 300 gigawatt of wind, we will have a very structural hole in our grid, which is long-term seasonal storage. And that is where hydrogen comes in, especially if there is some use case there. But then there are competing technologies like coal gasification, underground gas storage, which are competing with it, which is sort of will become more clear as carbon capture becomes clear. So there's a jury out on this market right now. So today, what we are seeing is that BESS is getting more and more efficient, and in the market, the prices are going down. There is quite a bit of like what happened in the solar industry some time back, that the prices went down so much that it distorted the pricing expectation in the market. The same has happened in the battery. So that's impacting in general the storage market's profitability and expectation. So there is a bit of a setback to the storage market in the short term, but we are quite clear also seeing that as the penetration of wind sector increases in the grid beyond what it is today, and as coal thermal do not get added, we will start seeing some of these projects coming up. So right now there is a requirement from the CEA to have seasonal storage of 10 gigawatt, and there is no other technology apart from hydrogen that could do that very well right now, especially if you use salt caverns. But there is not quite a bit of traction on that so far. So it remains as a market where the government requires to come up with a clear policy. So that's what we wanted to present. What's the state in the market overall? What are the industrial applications? Where does glass come in? Where would small batch size come in? What's happening on the overall system in the storage market? What are the different sizes and numbers that we are talking about? What is inhibiting this market, and the price distortion that is happening in the battery market? So that's where we are. And so that's what we wanted to present today. Over to you, Nish.
No, Siddharth, thank you very much. I think it was quite comprehensive. Already had 2 requests for your presentation as this is going on. But before I bring in Carlos, I think Carlos is our next speaker. A few things I want to understand is when it comes to these applications that you're talking about today, right? When green hydrogen becomes more affordable, I know these industries are buying it at $10. Do you think that there's potential for larger adoption in these sectors, like especially looking at glass? Or do you think wherever there is an hydrogen application, it's already being used? And if prices come down, you won't see further adoption?
No, I think the there is, wherever there is a small batch size right now, it's very hard to get gas in India, and it's very expensive. So there, some of the companies have started to move very small, batch size discussions and figuring that out. The larger adoption will require some sort of, carbon premium, which is, can we know, is a market that is struggling right now, or some sort of government derivative to come in to sort of push this market a little bit forward. But the adoption will be there. I mean, as the costs come down with some of this blending happening, will becoming more and more clear, especially, where the syngas production use cases possible, those will definitely adopt first. So my view is wherever it's a processed gas, small batches, that adoption will start. The applications where that is a feedstock, you require a mandate. Wherever there is blending and firing, that requires a more comprehensive overhaul. So in the process and syngas part, especially where it is being used, where you can carbon capture with it, that will also move ahead quite a fast. So one of the applications niche, just to sort of also give a perspective, is that what we have seen in the European market is that there's a lot of discussion around how we can upgrade some of the weaker streams of biogas or natural gas and improve their quality using some electrolyzers and doing that. So that is also great. So these cases are developing right now, but mass adoption would be something that is um, requiring a cost reduction or a mandate.
Wonderful, Siddharth. I think if anybody else has questions for Siddharth, we can spend a few minutes discussing this. So if anybody has any questions, just put your hands up. We'll enable your mics if it's disabled, or just drop questions in the chat box. Meanwhile, if Carlos, if you're there and you can come, if you can put on your camera. So Carlos and his company, they've been looking at using hydrogen for stationary power purposes, right? And I think it'll be very interesting to hear from him and how they're preparing for this, huge adoption of green hydrogen. But before I bring before I bring Carlos back, I have a hand up. It's from Rajan. Rajan, so if you want to speak your question out.
I wanted to add a information in what Siddharth had just presented. Actually, decarbonization is happening in many industries, in glass companies like Borosil and all. They are using HHO electrolyzer, same electrolyzer but without membrane, and just depolarizing the water bond into HHO, and it reduces the energy requirement, the gas requirement by 15 to 20%. And it is very cost effective, and the payback period is hardly 6 months. Already, Borosil has implemented it.
Thanks very
And
much,
many
Rajan.
other industries are doing it actually. But since the glass industry was being discussed, so I gave example of
No,
this.
thank you very much. I think it also highlights the fact that there is immense potential in green hydrogen applications, right? And I think it's only a matter of time when we reach price parity, we will see a lot of such cases and innovative ways of using green hydrogen in various applications. But let me introduce Carlos. Carlos has been well, Hina, I'll take your question before we move to Carlos.
Sir, my question is that how much amount of hydrogen is required in the polishing process?
The polishing process of glass.
Right. So the amount of the
Um,
hydrogen, how much hydrogen
Interesting.
required?
I don't know, Siddharth, would you be able to come in on that?
No, I don't have the number on top of my mind.
Okay. Well, Hina, I think we should save this question for our speaker who's supposed to come next. We're just trying to get him back online, but he will be able to answer because he's been working with the industry on this. So, Carlos, over
Okay.
to you, Carlos. You take us away, please.
Sounds good. Nishan, thank you very much for that introduction. Let me share my screen. So let's see. Can you confirm you see the presentation?
Yes,
All right.
and it's moving as well.
Everyone, a pleasure to meet you and thank you for being here. I'm Carlos Pabon. I am Business Development Manager International for 2G, based in Germany. I am I'm currently in Spain, and it's a pleasure to be able to talk to you and tell you a little bit more about our experiences with 100% hydrogen gensets. I'll start very briefly just with an introduction of our company, but I'll jump very quickly into the technology and into our use cases. The focus of this webinar is precisely the use case of green hydrogen. So I will not bore you with side topics for too long, but very briefly, as 2G, we are a leading international supplier of internal combustion engines for stationary applications and also of combined heat and power plants for distributed generation. We start at 20 kilowatts per unit and go up to 4.5 megawatts per unit. We have been in the market for over 3 decades, or actually almost precisely 3 decades. Next year, we're going to have our 30th birthday. Founded in Germany, we're still headquartered in Germany, but precisely from all our international markets, India is a very interesting one for us, and I'll share a couple of updates on that regard. We're still, our manufacturing is still located in Germany. Nowadays, we're more or less 1,000 employees. We execute more or less 350 million euros in projects every year. We have delivered more or less 9,000 systems to 60 countries around the world. Of those 9,000 systems, let's say that almost half are running on sustainable fuels, such as biogas, for example, at wastewater treatment plants, industrial or municipal, at landfills, or at biogas from agricultural operations. Then we have delivered some 3,000 projects running on commercial and industrial applications. These are usually larger systems running on automotive factories, on food and beverage, on plastics, paper. And then finally, we have supplied more or less 1,000 or 2,000 projects, between 1,000 and 2,000 projects of what we would call special gas projects, including associated petroleum gas, flare gas, and of course, hydrogen, which is the topic of today's conversation. As you have probably heard in the industry, when we talk about hydrogen, most statements are forward-looking statements of what the industry and the world is really preparing themselves to do. But we're very happy to share that our customers actually, and 2G together with our customers, we started already a long time ago working with 100% hydrogen. Our first unit was delivered over 10 years ago, over a decade ago, to the airport in Berlin. And nowadays we have delivered over 35 systems running on 100% hydrogen in North America, Canada, and the US. In Europe, in Germany, of course, many plants, and also in Asia. We do not yet have a 100% hydrogen unit in India, but closest to you, yes, in a few countries in Asia, we already have units operating. That may be just very briefly on 2G globally. When it comes to 2G in India, as mentioned, from the 60 countries where we have delivered systems, India is a very special market for us. From our experiences in all these markets, we understand which is the best way with which we can be competitive. So as it has been, let's say, a piece of confidential information for a bit of time, but now we're able to talk about it. 2G has approved internally to build a production plant in India. This is going to be used to serve multiple markets where the core technology is still going to come from Germany, the internal combustion engine, but everything else is going to be locally integrated with our know-how, of course, locally integrated and locally supplied, not only for India, but also for other markets. So we are placing a big bet on the Indian market. We have already started delivering our first units for a few groups. mainly in the biogas sector, but not only. All right. With that, starting to go into the technical portion, something that will interest you. As a brief outline of our product portfolio, we start at 20 kilowatt units, go up to 4.5 megawatt units. So we do distributed generation. When it comes to hydrogen, as you can see on your screen, we have dedicated product lines that are able to operate with 100% hydrogen. Those engines start at 100 kilowatts, approximately 115 kilowatts precisely, and go up to 750 kilowatts per unit. And I'll show you an overview in a moment. Our strength lies on gaseous fuels. We don't do anything with liquid fuels. We don't work with diesel. Everything we do is with gaseous fuels. And within that, and because of that, every single one of our products is specifically dedicated for each project that we are able to execute. Gases are always different. Well, not always, but often different. If you take pipeline natural gas will be similar, let's say, in many places in Europe. But even when you take pipeline natural gas, it may contain traces of or larger quantities of other gases. And that's, let's say, still the simple case. When we go to more complicated gases, biogas, waste hydrogen, for example, every gas is different. And hence, we always optimize the engine for the dedicated gas that it's going to operate with. And not only, we also optimize the engine for the specific site where it's going to operate. So, for example, beyond our standard versions rated at ISO conditions, so 25 degrees centigrade, and sea level altitude, we also have, for example, high altitude versions with which the engine is going to deliver the same power output at 2,000 meter altitude that it would deliver at sea level, or it will deliver the same power output at 40 degrees centigrade as it would deliver at 25. So we have special versions in terms of altitude, site conditions, altitude, temperature, but also in terms of site requirements, emissions, for example, NOx emissions, CO emissions. So we're able to optimize the engine for each project, and that includes, of course, the fuel gas. And this is a good example. As you can see on your screen, we have different versions. All of these different line items are the same base engine. Here we're talking about the engine that we would usually call our Genitor 412, type 4 engine with 12 cylinders. And as you can see, depending on the gas that we're going to utilize, we change the operational parameters of the engine, the compression ratio, the brake medium effective pressure within the chamber, which changes the output that we can reliably guarantee, and also the electrical efficiency. This is just as a brief example. And this, let's say, gas engine technology is half of our business, half of our core business. The other half of our core business is system integration. So what you see on screen, on green color here on your screen, is the core of the technology, the gas engine. But beyond the gas engine, we're also able to deliver fully integrated plug-and-play type cogeneration systems or gas-to-power generation systems for different applications. And in the bottom of your screen, you see a very interesting example where the customer, this was an industrial customer, they needed electricity. So we provided on the right-hand side the power generator, but they also needed steam. So we provided a heat recovery steam generator, but they also needed hot water. So we provided an additional heat exchanger for the production of cold water, of hot water. And ultimately, they also needed chilled water. So we provided an absorption chiller to recover the last bit of portion of thermal energy. With this, we had an efficiency at this site of over 90%. That was, let's say, still an introduction into the technology, but not only specific for hydrogen. Now we jump into 100% hydrogen systems. As mentioned, we have delivered this over 35 systems to date. Our first system delivered over 10 years ago in 3 different continents. Our product range, you can see on your screen, starts at 115 kilowatts, goes up to 750 kilowatts. And all the units that you see on your screen, we have already delivered. These are already operating on the field in different countries. So how does the technology look like? What you see on your screen right now is a standard gas engine. A standard gas engine utilizes, let's call it a carburetor. It's not precisely a carburetor, it's a fuel air mixer. But let's call it a carburetor. A standard gas engine utilizes a carburetor, which, as in any other engine, it mixes air with combustion gas, with fuel. This can be natural gas, this can be biogas, for example. It turbo compresses the mixture and it goes into the engine. It also intercools the mixture and it goes into the engine. And we produce electricity and we recover the heat. This is how a standard gas engine looks like. Then, with our technology, we are able to utilize fuels containing up to 40% volumetric content of hydrogen, still largely utilizing what we call a standard gas engine. We will modify some components on the fuel intake system, but up to 40% hydrogen, we're still able to utilize a relatively standard gas engine. The change comes when we go above 40% hydrogen and when we want to utilize 100% hydrogen. In the case of 100% hydrogen, what we do is we get rid of the gas mixer. We no longer utilize the carburetor. And we use a different technology called direct port injection, with which we still turbo compress the air, but the only place in the system where we have a combustible mixture of hydrogen and air is in the combustion chamber directly. This is done from a perspective of security and safety, operational security, operational safety, but not only. It also helps us better manage the combustion, achieve higher efficiencies. There are different reasons for us to utilize a direct port injection system. And let's say that that is the main change between, the main technological change between a standard gas engine and a 100% hydrogen engine. And these engines, as mentioned, we have deployed them in the field already. But this actually for us is the simpler case, let's say. The more complicated case that we have also deployed in the market is a fuel blending engine. So not a system that is going to run only with 100% hydrogen or only with 100% natural gas, for example, but an engine that is going to blend those fuels as much as needed. So a system that is going to be able to run from 0% up to 100% hydrogen. As far as we know, there is no other company currently in the world that has deployed these systems in the number that we have deployed, over 30 systems, as mentioned. As far as we understand, we're the only company currently doing this already with the on-field experiences for what regards internal combustion engines. And here what we do, basically, we combine the standard system with the gas and air mixer with the direct port injection system. So we have, let's say, the two systems that you saw before combined in a single one, and of course, managed through the control system that is also a technology, or a proprietary technology of 2G. With that, as mentioned, we are quite unique when it comes to internal combustion engines. Of course, fuel cells are also available on the market to run on 100% hydrogen. We often find ourselves competing with fuel cells in projects. The characteristics of the systems are completely different. I wouldn't go into too much detail during this presentation, but if you want to, if you have a project in mind, if you want to have a look at engines versus fuel cells, we can definitely look into that in more detail. I would need a little bit too much time to go into that topic right now. But let's say usually the starting point is the capex. Fuel cells can have a capex that is 5 times to 7 times higher than gas engines. So usually what has been the limiting factor for gas engines running on hydrogen is that technology was not available. But since the technology is indeed available by 2G, we have been able to place ourselves in the market quite well. But in any case, glad to discuss that further beyond this presentation. Going into a few use cases. I'll just present you a few cases that I find to be interesting because the applications all of these with 100% or very high content of hydrogen are still very different. For example, in this case, we are part of a 1 gigawatt solar park. At that time, it was the largest solar park in the world. It's not anymore. Mounted in Dubai, in the United Arab Emirates, where hydrogen and our internal combustion engine is precisely being used as energy storage. So basically, during the day, the electrolyzers are producing hydrogen, and the hydrogen is being used basically for transportation fuel directly. But there's also a hydrogen storage tank during the night when the solar panels are not available. The stored hydrogen and our internal and our gas engine are being utilized to produce electricity at night, mainly feeding the needs of the project, but also exporting into the grid. So here, a 1 gigawatt solar park. Then we jump into a way smaller application, into an industrial application, where in this case, the customer, talking about circular economy, the customer is actually producing hydrogen storage tanks, and they utilize a 100% hydrogen engine to run on green hydrogen that is produced on site. And in this case, we're not only producing electricity, but we're also producing heat. Hence, we're utilizing a fully decarbonized fuel with an overall efficiency close to 90% to produce both electricity and heat to be used at the manufacturing process of hydrogen storage tanks. If we go into an interesting case, again, different from the previous ones, we go to the UK. Some years ago, we delivered the first 100% hydrogen engine operating in the UK, and the sites of interest are actually two. In this case, the green hydrogen is generated with marine power at the European Marine Energy Center, but there is no immediate use for the hydrogen at that site. So what is done is the hydrogen is compressed, trucked, and taken to a nearby airport in Kirkwall, and the airport has its own cogeneration unit and utilizes 100% green hydrogen to produce electricity and heat for decarbonized airport operations. An additional interesting case in the industrial sector is at Toyota's headquarter factory in Toyota City in Japan. This is, let's say, conceptually somewhat similar to what I was showing before on the hydrogen storage tank manufacturer. This is an industrial application where the customer is utilizing not only the electricity, but also the heat in an industrial process. This case is entirely different from the previous ones in the sense that all the previous cases that I was showing you are green hydrogen from electrolyzers. But in this case, we are talking about a semiconductor manufacturer from Taiwan. They have a process gas that they were flaring for a few years with very high hydrogen content, 97% hydrogen. It's a little bit variable, but around 97% hydrogen up to 99%. And they weren't able to utilize it, but then our technology came across, and basically they are now utilizing that waste gas as a valuable fuel that comes for free or even at a negative cost to produce electricity and heat with free fuel for their manufacturing process. So again, circular economy, utilizing a waste fuel, 97 to 99% hydrogen, and converting it into valuable fuel for cogeneration. And then finally, at the beginning, I showed you how we can be part of a 1 gigawatt solar park project. In this case, we're part of a 20 megawatt wind park in Germany. And this case is quite interesting because here we have a multiple set of uses for the green hydrogen that is produced by the wind power plant. Here we also have a storage tank, and you have to imagine that the storage tank has different outlets. One outlet goes to a district fuel network where the hydrogen is blended 10 to 20% with natural gas and distributed to the local residents, and the local residents utilize partially decarbonized fuel for cooking, for hot water purposes, etc. Another outlet of the hydrogen storage tank also goes to blending with natural gas, 10 to 20%, and that gas goes to the brewery. You can actually see the yellow tower here on one of the pictures. Goes to a brewery, and they have their own cogeneration system supplied by 2G, where they also utilize partially decarbonized fuel to produce electricity and heat in their manufacturing process. And then finally, there's a third outlet of that storage, which is a one hydrogen system, which and heat. The heat is the electric heating network, and the electricity is interesting because the German market is a highly sophisticated market. This unit is directly connected to the electricity market. I don't remember if it's the day ahead or intraday market. And basically, the plant monitors the electricity prices, and when the electricity prices are high enough, it gives the go to utilize hydrogen to produce electricity. So we already see, in line with the previous discussion, the previous presentation, we already see some applications that are passing from technology demonstration towards commercial operation, and we have been happy to be part of those projects again for many years now. And with that, Nishant, I hope I have been somewhat respectful of the time. That has been my presentation. I'm happy to reply to any questions that you may have.
Sorry, thank you very much. I think what you've done is you've showed, several cases where green hydrogen in the future could be utilized, right? Because everybody is questioning, where are the applications, but you're showing that, there are so many more versatile applications. But I think there were two questions that came in for you. One was, on your Dubai solar plant, the question is, was the use case of hydrogen for auxiliary consumption at the solar plant?
Mainly, and not only, in the sense that this is a very interesting project. It includes standard solar PV modules, but also concentrating solar. Actually, on the left picture, you can see the tower for the concentrated solar panel. So this is a project not including only a green, the solar park itself, but also a green hydrogen generation project, the electrolyzer. So I'm saying this just to say that there are substantial auxiliary loads on site. So correct, a lot of the electricity is used to supply the auxiliary loads, but also part of the electricity, when there is not sufficient demand on site, is exported into the grid. But we're talking about, relatively small amounts compared to a 1 gigawatt solar park. It's very, very small amounts.
I think there's somebody in the audience who would have loved to see that CSP plant there in the background. The next question is, in the solar plant where hydrogen was used as a storage medium, what did the plant do with the heat component which was released when it is burnt in the generator?
In this case, the customer is not utilizing the heat, as far as I understand. There's no heat recovery in this case, so this is just power generation. There are different use cases for the heat. It can be used in such a location. For example, it could be used for cooling. We have executed such projects where this is more common for turbines. Why? Because turbines lose power quite dramatically with higher temperatures. Engines do not derate that, our engines do not derate that dramatically when the temperatures goes up, but still certain customers do not want to lose any power even if they're at 50 degrees centigrade. So what we can do is produce heat to produce chilled water with an absorption chiller, and then pre-cool the incoming combustion air. So we do combustion air pre-cooling, we maintain the combustion temperature, the combustion air temperature minimum, and therefore we improve the power output. That is one use of the heat if there is no direct users of the heat on site. Another use of the heat depends on the electrolyzer that is used. There are certain electrolyzers that benefit either from the hot water that is being produced by the engine or by steam, so we can include a heat recovery steam generator. They preheat the incoming water that is then split into hydrogen, and thereby they increase the efficiency of the electrolyzer. So that is another possible use for the heat, but these are things that are not being done at this site. Just to mention a couple of examples.
Thanks very much, Carlos. One last question before we move on to the next speaker. How does your genset compare financially to a battery energy storage system?
And that's a very good question. That's a very good question. And I would say that it doesn't really depend on the engine only. It depends on the whole system, and it depends on the use case. So, of course, I cannot give an answer just like that, because it will depend on the characteristics of every project. But I can say that the considerations are always, or usually, financial, which is the question, but not only financial. They often go beyond the financial matter. For example, the availability of batteries, uh, the materials used in the batteries, and the availability of those materials. This became evident during the pandemic, where there were several shortages of battery supplies, as you probably are aware. So the financial portion is a factor, but it's not always the only factor. Comparing chemical storage with hydrogen versus battery energy storage is it goes beyond the financials only. Nothing that we can really address or analyze during the presentation. But yeah, gladly, if you have my contact details, we can discuss that offline whenever we have a little bit of time.
Not only that was a very good question, that was also a very good answer, Carlos. And thank you very much for taking the time out. I think you guys have a lot of potential in the market, especially considering the versatility of your products and your lineup. And I think, India would be a great market for you as well. And I'm glad that you're looking at a lot of industrial applications. So with that, we'll move on to our next speaker, but
Thank you,
please stay
Nishan.
on the call, Carlos. And we'd love for you to stay back and answer any more questions that come in. You already have
Sure.
some on the chat box. You can have a look. But in the meantime, let me bring in, I think, Dr. Janvit. And Janvit, I'm sorry, I'd rather not say the last name and mess it up. So I'll let you introduce yourself. I do understand you're a researcher, you're a doctoral research associate at the National Institute of Chemistry in Slovenia. But why don't you, give us a few words about yourself, and then you can get started.
Yes, hi. Can you hear me well?
Yeah.
Okay, perfect. So my name is Jan Vitržan. I work here in the National Institute of Chemistry in the D13 department for chemical reaction engineering. And we are very, very involved here in, let's say, Central Europe in all of these different hydrogen initiatives and hydrogen projects that are running, and different hydrogen valleys. Blaz is the one who is spearheading most of these new project acquisition and project proposals. Me, on the other hand, I'm, let's say, the operative person here leading the projects and also finishing the project proposals. And maybe if I just start sharing. And hopefully you can see the presentation. Yes, we have, as I mentioned, different projects. This is either for hydrogen production or hydrogen storage in liquid carriers such as ammonia, or combining hydrogen production with carbon capture and utilization, such as methanol, ethanol, and higher C2+ projects. And we are mainly, of course, we are completely focused on electrification of all of these processes. So, moving away from steam-based reactions and steam-based reactors, and completely focusing on electrified reactors. So currently at the department, we have more than 40 active national and international projects, just over 30 European Horizon and some other projects. We have several professors here that offer several courses at all levels of this tertiary education, so doctoral education. And our motivation is, of course, all of the hydrogen that is currently produced with the steam reforming, methane steam reforming, which is 2,400 tons. And since 1.2 kilotons are used in the production of hydrogen, that's a big hydrogen peroxide, that's a big project for us. And the rest are used in the steel and glass making industry, where we are very active, and we have couple of projects that I will also describe later on this topic. So where do we see hydrogen use currently, or where we are involved? So generating high temperature heat, such as in the steel, cement, brick, and glass industry. What is missing here is also in the aluminum industry. Additional uses are, of course, in transport mobility. Where we are active is the large scale, this hydrogen valley. I will talk about this a little bit more later. This is like, let's say, Central Southern European coalition of Slovenia, Italy, and Croatia. Blaz just started a hydrogen center with the University of Graz. You can see this on the right hand of the slide. And we are, of course, involved in the national hydrogen roadmap that is being prepared under NECP. This is the North Adriatic Hydrogen Valley that I was discussing before. The budget currently is 25 million, with a leverage effect over 700 million euros in investments when we take into account all the partnership with the 34 organizations. It is an integrated cross-border cooperation, starting everywhere from hydrogen production to hydrogen pipeline installation and hydrogen utilization on site. So the entire renewable supply chain. And the idea is to exchange more than 20% of hydrogen annually. That would be about 5 kilotons per year, which is, as we all know, a lot. There are, of course, 3 strategic sectors that I also pointed out earlier. So industry, energy, and transport. And within this, we have a plan to test or build 18 pilot projects or testbed projects. So another big part where I am right now involved a lot is the this Central Sava region, which was included in this Just Transition Fund. And the idea here is to deploy a 9 megawatt electrolyzer, which will be focused on local energy. So just making a completely renewable, or let's say a completely hydrogen-based community, and of course include the local industry, which is the glassmaker Steklarna Hrastnik. And the idea is that also in the next 3 years, Steklarna Hrastnik will replace 25% of its fossil fuel use by hydrogen production even now. Another thing being developed within this Just Transition Fund is the Center for Development, Demonstration, and Training of Carbon-Free Technologies. The, let's say, main part of this project, or the project, will be split into 2 major laboratories. One will be the laboratory for battery technology and battery energy storage. The other part is for hydrogen and CO2-based technologies. And the idea is for this center to be a bridge to overcome the death valley that we currently have somewhere between TRL3 and TRL6 levels. So it will be upscaling laboratory technology that is developed here at our department at the National Institute. The center will be developed within the, of course, within the National Institute, but it will be a separate entity that will, let's say, focus mainly on research and development of pilot plants, so moving up to TRL6, so that we bring the technology closer to our industrial partners and, you know, pique their interest, because we found that here a big problem is that since we develop, or when we develop the technology to TRL level about 3, it's not easy to convince our industrial partners to move into some pilot research. plants, and the idea of this center is to bridge this gap. Another big part of this center will be also training, so either getting master students and PhD students to work at the center and getting hands-on experience and knowledge with hydrogen-based technologies, get them up to speed with the latest trends in research, which will, of course, enrich the educational programs at the university level, but also a big idea is to have a competent workforce really focused on hydrogen-based technologies that is available to our industrial partners. Of course, the center will integrate into international projects, some that will be applied through the center and some that will be integrated within the National Institute. We are already connected well with the industry, with industrial partners. We have several projects in the works that will focus on either hydrogen use or just shifting into a greener and more renewable mode of operation. And of course, establishing new infrastructure, as I mentioned in the beginning, the connecting between industrial and academic partners to move this innovation to higher TRL levels and hopefully integrate it into the future of industry. This is the laboratory. There will be over 1,600 square meters of brand new laboratory space. Just for the equipment, the investment is going to be 20 million. And we will have, of course, everything to test out the either catalysts or electrolyzers on the laboratory level and move them to higher levels. And not just for the CO2 and hydrogen technologies, but also for there will be a massive battery testing facility that will be also semi-industrial scale TRL levels up to 6. So one of the projects that also resulted in a pilot plant is the methanol synthesis. We were collaborating with the cement industry, and this project was actually spearheaded by our department and ran all the way from TRL levels 2 to 3, where we designed and tested out the catalysts in our department, made predictive multi-kinetic multi-scale models. Of course, the most important in this part being the kinetic models, and integrated it into a methanol plant. And this pilot plant is already operating and generating, I'm not really sure, but several tons of methanol per year. Another project that we are very invested in is the Oracle project. And this project focuses on hydrogen storage, so in liquid fuels, as we found with the project before. But this one is focusing on ammonia. And here we are reimagining the Haber-Bosch process, where we are trying to move from these localized, massive ammonia production plants to make it more dispersed and more, let's say, delocalized ammonia production, very small scale, but more in line with the shifting nature of renewable energy, where we integrate it with renewable power sources such as wind and solar, and try to design a reactor, an electrified reactor that operates dynamically. So we have this very rapid response of on and off. The technology that I developed here with colleagues from the Joseph Institute is induction-based catalysis, where we have the catalyst that is reactive to an external magnetic field. So we really have this very fast temperature increase, and we can really start the reaction in 5 minutes, and we see ammonia production in 15 minutes, which really shortens the necessary time. So this is just a general overview of how the hydrogen valleys are, let's say, designed, how we imagine that the hydrogen valleys will focus, will function. So we have next generation market development. This is just developing the market for hydrogen utilization, and of course integrated projects that kind of cover the whole hydrogen economy. So from production all the way to storage or utilization in transport and energy. And on the right-hand side, you can see what are our main drivers are. Mostly climate action, some industrial policy, job retention and creation, of course, strategic investment, energy security, and others. Now I would move on to some actual projects that I am working on, that we are leading or involved in. The first is the H2 Glass hydrogen project, European project based on hydrogen. The project is worth just over 32 million euros. The idea here is to decarbonize the glass and aluminum industries. And the project focuses on everything from policy creation all the way to burner development, the electrolyzer development, and of course relevant industrial tests where the developed burners will be tested in an actual glass melting furnace in Steklarna Hrastnik, and then they will be also tested in some pilot furnaces in by Vetro Balsamo and Staraglass. And additionally, the electrolyzer will be mobile, so then we will also move it to Hydro, where they will also try to see how just aluminum metal reacts if it's melted with a hydrogen burner, because we all know that melted aluminum and higher water content don't really mix all that well. The second project is Hyper. I mentioned in the beginning that a very large part of hydrogen currently produced in the world is used in hydrogen peroxide formation, and here we are trying to develop a reimagined hydrogen production for and integrating it with reimagined hydrogen peroxide production using different, let's say, intermediates and electrifying the reactor, so that we really reduce this reliance on either on fossil fuels, and of course improve the integration with the shifting nature of renewables. The EcoDuct partner is also a larger, let's say, conglomerate where we are joined by Saint-Gobain and Total Energies. And in this case, we are reimagining or trying to electrify the process of sulfur formation, or where we convert CO2 to carbon monoxide. Carbon monoxide reacts with hydrogen sulfide to produce carbonyl sulfide, which is then converted using electrical energy into sulfur and carbon monoxide. And this carbon monoxide can then be reutilized in the original process, or of course it can also be valorized into either methane, methanol, or some other hydrogen carriers. So besides Oracle, we have a couple of other ammonia-based projects, and we know that ammonia is a So equilibrium limited reaction, so it's thermodynamically limited. And in this project, in this case, we are developing or testing out absorption enhanced ammonia production, where we are focusing on manganese chloride as the sorbent, where we are trying to improve the single pass conversion of hydrogen and nitrogen into ammonia. And additionally, the second European project on this topic is where the sorbents we are developing within Hystrom are then integrated with a plasma catalytic reactor, where we are trying to do absorption enhanced plasma catalytic ammonia production. Now, all of these processes are electrified, so that we really try to shorten this time from the onset of, let's say, a surplus of energy to actual production, to reduce this time as much as possible, so that this dynamic operation and this applicability with renewable resources is, let's say, improved as much as possible. Additional projects are the Reveal project, where we are considering using aluminium metal and reacting it with water or water vapor to see, let's say, a modified power to gas technology that is power to aluminum. And so in the summertime, when we have more solar energy, we use some electrolysis or some reduction process to reduce aluminum oxide into aluminum metal. And then in the wintertime, or when we require heat and surplus of energy, we react aluminum metal with water vapor. We get aluminum oxide, a lot of heat, and hydrogen gas. And the approximate calculation is that the average average family home would require about 400 kilograms of aluminum per year. The Dynamine project is basically just utilizing neural networks and machine learning to see if we can automate and robotize machines and strategize to enhance safety and productivity, and to increase practices or promote practices that are carbon neutral in transportation and increase energy efficiency. There is this Vanguard initiative where the idea is to install a 40 gigawatt electrolyzer. And as you can see here on the bottom right, we are one of the partners co-leading this initiative. And another very big project that we are also working on with the Steklarna Krasnik, so glass making, is what if we don't use hydrogen, and if we use renewable electricity directly? And in here, in this project, our part is the whole techno-economic analysis and life cycle analysis of what happens if we not only don't use natural gas, we don't even use hydrogen, we just use electrodes and just melt the glass directly with electricity, and how this would compare with just using hydrogen gas burners like in the H2 glass. I will try to speed this up a little bit. So what our department does is we go all the way from quantum mechanics, so from DFT level in where we have electrons and atoms, to molecular dynamics, which is kinetic Monte Carlo, to the mesoscale, where we have coarse-grained kinetic Monte Carlo, and also direct kinetics that are based on experimental results. We have the macro scale, which is computational fluid dynamics and correlation equations. And all the way up to process simulation in an industrial setting with software such as Aspen or similar. We have several options available. The Ajman High Performance Computing Center and the High Performance Computing Center Vega in Maribor, that is relatively new. This is, let's say, a few approximations of some CFD models that we developed and actually calculated within our department. We are involved in the massive national project Hybrid, where we have 7 or 8 industrial partners collaborating with all the major academic institutions, the faculties, and the research institutions here, where we are developing several hydrogen technologies and see how they integrate within existing industrial practices and the industrial standards, such as in steel formation and steel softening in the aluminum melting, glass melting industry, and the pipelines and hydrogen gas pumps. And of course, all of this is supported very well with different national companies such as Devasoft, Steklarna Hrastnik, Geni, Iskra, and of course also international companies such as Honda, Total, Evonik, Neste, and Johnson Matthey. And with that, I would like to thank you for your attention. I was a bit long, but hopefully you did hear everything you wanted to hear.
Janvits, thank you very much for that. And I think it was a lot more than we were expecting, especially the breadth and depth of, the work that you're undertaking. And I think, there are so many more stakeholders here in India that would be interested to hear about what you just explained to us. And I think this should be done on another call as well. But if there are questions for Janvit here from the audience, please, feel free to raise your hands or put questions in the, in the chat box. We had a question earlier, Janvit, just before you joined, from someone called Hina on how much hydrogen is actually used in the glass making process, right? If you have any numbers on that, and in particular on the polishing aspect.
Well, currently, as far as I know, there are no, let's say, industrial level companies using hydrogen. What we found within the H2 Glass project is that with the existing technology, we could use about 15% of, let's say, 15% of natural gas could be replaced with hydrogen without any detrimental effect. And it could be used as is. But of course, we are focusing on just completely replacing the whole energy requirement that is currently input by natural gas with hydrogen. But again, this is also, it's kind of hard to say because it really depends on the furnace that you have. If you have oxy-fuel burners, or if you have so just natural air burners. If you have a regenerative furnace, we found that this can also be an issue, right? Because using a regenerative furnace, then the gas flow that shifts, you have a different thermal dynamic, and so it's not a simple answer.
Well, I think I have, somebody here who's been working on hubs in India and has been involved in several global projects. Rolf, if you're still here, if you want to come in.
Yes, switch on my video.
Yes, wonderful, Rolf. Rolf, you've seen Janvit and they presented something on the hubs. Are there any lessons we can take from, the work that they're doing and, some of the other applications that, he presented on here today?
If Janvit could go back to the slide, because he prevented so many, quickly went over it, so I didn't have the time actually to understand the details. And I would like to know more of the details, actually. So if you could jump back to the slide.
I think Janvit, you are on mute. If you can unmute, that would be great. Thank you.
Okay. Yeah, sorry, I just had to share the screen again. So where do we, which
On
slide?
the hubs, Janvit?
So no, wait, this was before.
I think the
You
hubs
mean
came in before.
it's this one, right? Hydrogen valleys.
On Hydrogen Valleys, correct. Yes. Okay, we're here. And even before Rolf can come in on any particular question, can you give us some insights on how this, how the valley is being funded? And is this an existing industrial cluster that you are looking to convert into a valley, or is it a greenfield development?
Actually, it is a greenfield development, but it is also a cluster. So of course, it's open also for other companies that are constantly joining the cluster. But for instance, our department and Steklarna Hrastnik, we constantly apply for these types of projects together. And there are some other partners that are in our applications, let's say 90% of the time. So it's, let's say, half and half. Some of this is funded by, of course, the European Union, but also there are a lot of these projects and a lot of these initiatives that then are also funded from the industry a lot. But mostly, I would say it's funded from the European Union.
And Janvit, in terms of some of these other industries looking to uptake green hydrogen, which are the industries you see coming as front runners, and especially those industries that can absorb the huge difference in price?
Well, that really depends on the how much the CO2 tax is going to be. Right? I mean, if the CO2 tax is going to be increasing, hydrogen might. I think if it increases by 100% as is, then blue hydrogen becomes competitive with natural gas. I think if it increases 300%, then even green hydrogen is competitive. But then it's always a question of, can you really use hydrogen? And currently, I think a lot of the industries are at that point, because I know that, so for the glass industry, the major problems that they have is just engineering, how to convert a traditional glass furnace into a hydrogen capable furnace, right? Because the hotspot moves, the hotspot actually, the temperature of the hotspot increases. You have problems with the regenerators. There are questions that are of an engineering nature, not of a chemical nature. On the other hand, the problems that the aluminum industry and steel industry is facing is if hydrogen, if there will be some hydrogen in the in the flue gas, hydrogen can penetrate into the steel, making it more brittle. And so then it is a question of, are hydrogen burners actually even applicable in steel industry, the ones that they use for shaping steel, right, softening it up? And the same question is for the aluminum industry, because if you have an oxy-fuel type furnace, right, where you're just combusting hydrogen and oxygen, then 100% of your flue gas is water, because you're forming nothing else. And high concentrations of water vapor are not really aluminum friendly. So this is another question where they have actual chemistry issues. Is hydrogen even appropriate? Can you even use hydrogen in these cases? So probably the transport sector will be more hydrogen friendly first, and for the industry there is still some, or quite a lot of research that has to be invested first until we find the say interested parties.
Well, Janvid, I think you're the first person who's answered that question, starting with the carbon taxes. I think that is the very reason, we're going to see green hydrogen, accelerate its adoption in spite of the price differential. Rolf, if you have anything that you want to ask.
Yes, having to unmute first, yes. Perhaps just to understand practically, thank you for the considerations on the different carbon taxes and also on the industries and the flue gas being on water vapor. That's just very practical. Thank you. I'll remember that. You had written here now, leverage effect of over 700 million investments. Which companies or which sectors would be making those investments? So not companies, but the sectors, to keep it confidential.
As I mentioned, like here on the end, so these are all our current partners, and a lot of these projects, such as the one that I mentioned, the Ecoduct, is also quite a big part of that project is funded by Total Energies, right? For the sulfur production technologies. So all of these companies are very interested in developing hydrogen technologies or just making their current projects more, or current modes of operation more green, more renewable. So this leverage 700 million, I think this was Blaz's estimation, and I think this is considering all of the investments that will then be also made from the industry, where we start moving from TRL3 to TRL6 levels, where our industrial partners will be involved in the production or installation of pilot plants.
All right. And would your value be, just to understand, where would you be getting the renewable energy from? And where would then the electrolyzer in the industries then be based?
So I think this was a nice picture right here. So a lot of Slovenia looks like this, right? Where you have companies or industries and people living next to the river, down in the valley. And in this specific case, what one of the considerations is, one of the projects that we are currently developing is that you make a solar power plant on the very top of the hill, and then you run the power just down to the valley, where you remove the water from the river, electrolyze it, and then the first idea is to just put hydrogen into the existing natural gas pipelines and replacing up to 15% of natural gas with hydrogen. And that's the first idea. But then the idea is to slowly increase the photovoltaic, so solar power production, because we have a lot of this space on top of these hills and around.
Rolf, you're on mute, Rolf.
Thank you. All good. Yes, no. If I can switch to the Reveal project, I mean, this is a very cool idea to produce hydrogen from aluminum hydroxide and therefore releasing it. How realistic is this actually that this can be done? And on top of that at scale?
Well, this is one of those projects where we are talking about, where we have this leveraged impact. This was also a project that was co-funded by the local aluminium industry. So far, we are looking at how to consistently produce hydrogen and thermal energy from this. But as far as our calculations are concerned, this works really well. So aluminium reacts well. We are able to collect all the hydrogen. The reaction is very exothermic. So now it's a question of course, the electrolysis part, which still has to be quite developed, where we go from aluminum hydroxide or aluminum oxide, because it's a mixture of both. So where we move from these two into aluminum metal, and how to, let's say, grind the aluminum or have the appropriate form of aluminum metal to really consistently react it and get a stable output of power and hydrogen.
Okay, so this is still lab level or TR3, as you were saying, perhaps.
Yes, TRL3.
Okay, good.
We are waiting for this center in Zagorje to develop, so that then we can move into a bit larger levels. But so far, the industry is quite interested in all of these projects.
Well, these are cool ideas. So thank you very much. Anish, back to you.
Thank you.
Thanks, Rolf. Janvit, it was a pleasure, having you. And Carlos, I don't know if you're still there. If you're there, thank you very much for presenting everything 2G is doing, and Sidharth for giving us that great overview on what's happening in India in the hydrogen sector. There's a lot more happening this coming month in India. If there's people here in the country, you have the National Green Hydrogen Conference organized by the ministry next week. And the Green Hydrogen Organization is organizing a couple of roundtables there. And then the week after, you have the Renewable Energy Investment Summit, where we'll have a few other sessions on green hydrogen as well. But with that, let me bring this to a close. Thank you all for staying until the very end. And I appreciate everyone who's taken their time out today.